neither of you were here, so. My name, I think it's up there, I don't know. All right, so today I will talk about regularizations. So regularization means really to make infinities that we obtain in loop diagrams, to make them finite. So we will see that we have the kinds of regularizations that we have are called cutoff, Pauli-Villars, dimensional regularization, and also derivative regularization. All right, so the first and dumbest thing to do is cutoff regularization. So this is just saying that we have an integral and we just put an upper value for it. Right? So let's say we consider that the absolute value of the momentum has a maximum that we call lambda. Right? This is, well, this, to be more precise, this would be for UV divergences. And of course, correspondingly, for IR, divergences we would call a minimum value, perhaps epsilon. Now, there's an issue here. So the point is we do usually, I mean, the calculations that we do are in Euclidean space. So and in Euclidean space, writing something like this seems kind of okay because the space has the signature of the space is the same as the spatial one, so we have spherical symmetry. On the other hand, if we would do this in Minkowski space, then we would have a problem since space and time have different, appear differently in absolute value of p. So technically speaking, so this would break Lorentz invariance. Since, well, we're forced to treat space and time differently. So because of this, this is kind of little used. I mean, of course, if you just do Euclidean calculations, it's fine, but eventually you have to go back to Minkowski space. So because of this, this kind of regularization is very seldom used. And the point is, we have many kinds of regularizations, as we said, and we have to choose one of them. And which one do you choose? Well, depends. So if you want to do a consistent calculation, you should use symmetry that you should use the regularization that respects all the symmetries of the problem. However, it will also be that you don't want to respect the symmetries of the problem, in which case you will have a very hard time to prove that the final result is actually still invariant under those symmetries. So it's very cumbersome to do so. In particular, it will be cumbersome to use cutoff regularization. But you could do it. It's possible. All right. Okay, so let's see the simplest example of cutoff regularization would be to have just a one loop bubble, vacuum bubble like this, which would mean that we'll have and this, if I want to have both UV and IR divergences, that means that I have to consider a massless field. So in this case, I would have two such massless propagators, and then this would be integrated over, we consider now that we are in 4 dimensions, so d4 2 pi 4, right? So this will give a factor of the volume of the 3-dimensional sphere, the sphere in embedded in 4-dimensional Euclidean space, divided by 2 pi 4. And then from here we would have integral p cubed dp divided by p fourth. So this is just integral dp over p. And then this is from epsilon to lambda. So that means that, well, this thing would be log lambda over epsilon. And then, well, more precisely, this would be 1 over 32 pi squared. Now, you see now that we have indeed two kinds of divergences. When lambda goes to infinity, log lambda goes to infinity, and also when epsilon goes to 0, log 1 over epsilon also goes to infinity. Right? All right, so this is one kind of regularization. Now I want to remind yourself from very quickly from last semester that there's also a different kind of thing to regularize. There's these infinite sums that we've seen appearing in at one loop. So what we said last time is that if we have some action and we approximate it by some classical action plus a fluctuation, that is to say integral delta phi and here the inverse propagator, approximate inverse propagator, so integral d mu plus u double of phi 0. We've seen that then after some steps the Cartesian function is rewritten as, so this is then a Gaussian integral, right? Integral x squared over 2 times something, right? This is 1 over square root of that something, and so on. And then, but then you have to work on this result, and you can present it finally as a sum of En t over h bar, and then En is written as some h bar times omega n, And so finally, we find then, n plus 1/2. And finally then we find that there's a vacuum vacuum energy of h bar over 2 sum over n omega n, right? And this was also a divergence. In particular, this was a one-loop divergence in the sense that this was involved in just the first quantum correction to the classical action, and it involves one propagator. We said that in order to regularize this this divergence, you have several options. Well, first of all, really, this you cannot measure. You cannot measure this object. You can measure only differences. So in the Casimir effect, you can measure the difference between this object in the presence of some boundary conditions, like a condenser plate, and vacuum, so the space without anything. You can measure that. Or if you have a space with solitons, you can calculate the difference, for instance, between the thing with the soliton and the same thing without the soliton. So I should have said, well, let me be more precise. I want to say h bar n omega n. Now, it's here here if you look at this, you would say, well, I just put common factors, the sum, and then I have omega 1 minus omega 2. Well, that's not correct. That's one possibility, and that's one way to regularize this infinity. So this is really infinity minus infinity, right? And infinity minus infinity, you know, in principle can give any finite result. And one possibility is when you put as a common factor this, and this would be called mode, and you sum up to some n and calculate. But this would be called mode regularization. But the other possibility is to turn this into an integral over energy. So an infinite sum, you can always turn it into an integral. There's a way to approximate that. So you turn this into an integral and this into an integral, and then you take the maximum energy at this for this integral and for this integral, and that gives a different kind of regularization. This would be energy cutoff. Regularization. All right. Okay. So you also have these kind of one loop things to regularize with various possibilities of regularization, but this is a problem that is somewhat somewhat specific. There's very few people who work on this or think about this, since the applications are only to the theory of solitons. So let's consider with let's continue with regularizations of integrals of Feynman type. So the second regularization for these kinds of integrals is called Pauli-Villars. So Pauli-Villars is a way to smooth out this kind of hard cutoff regularization. In this one, you just stop at lambda. In this one, you think of smoothly turning off the momentum, right? So how do you do this? Well, if you have a propagator, now it's important that it depends on it has a mass. So if you have such a propagator, so one way is to smoothly turn off the momentum is to subtract the same kind of object, but with a mass that is very, very large, like lambda. So to be more general, what you do is you substitute this object with this minus. Now you could subtract several kind of propagator-like object, but then with some numerator. So and the point about this is that this is a little bit more general. So the simplest would be to subtract just this, right? But if you use this general one, what you obtain at large momenta is that this thing goes like let's say lambda the 2n. So here is I from 1 to n. Lambda to 2n over q to 2n plus 2, right? And the simplest case of Pauli-Villars is one propagator, subtract one propagator with very large lambda, in which case n is 1, and this goes like, well, lambda squared over q4, right? Okay. And the point about this is that, well, it could be that you have a very, very large UV divergence, and perhaps doing just that doesn't regularize it. I mean, it's not impossible for this to happen.
Why there is this important for the propagator to have a mass, the original?
Well, in this case, you will see. Yeah, here.
But the original one, the left there.
Sorry?
It's massless.
Yeah, that's what I mean. In this case, you will see. I mean, the point is, well,
Because it,
no, sorry, even in this one. So the point is, you have to have.
is it because of Gauge variance?
Let me think a little bit. No. Lambda squared minus n squared over q squared. No, sorry. Yeah. So for just one propagator, it's fine. It doesn't need to have m. But in the other cases, you need. Yeah, if you,
Is this gauge
yes,
invariant? Regularization. Gauge
I'm sorry?
Gauge invariant.
What about gauge invariant?
Is this regularization gauge invariant?
No, no. Well, we'll see later on.
Depends if I add max.
This is, well, yeah. So the gauge for gauge invariance was introduced a specific kind of regularization found by Toft and Veltman, which we will describe. But the first one to appear, the first theories to appear were things like Yukawa and so on, and full Fermi, those kind of theories. So in that case, people used usually Pauli Villars. Now you can still use that, but as I said, if you don't satisfy the symmetries of the problem, then you just have to work hard to prove that the symmetry is still satisfied for the physical result, because it doesn't look symmetric. The calculation of your, let's say, Feynman diagram doesn't look symmetric, but really, in the end, the physical thing you're supposed to measure, it's always symmetric.
What kind of symmetry would this regularization bring?
I'm sorry?
What kind of symmetry would this regularization bring, for example?
Yeah, in gauge invariance. Yeah.
Only the massive case.
Huh?
Breaks gauge invariance only the massive case.
Well, yeah.
If original is massive, then
Yeah.
Sorry, I didn't
Right. So
understand
let
all
me.
this.
So yeah, just a moment. So let's just be cool a little bit. So the first the first and simplest Pauli Villars is this minus this. So what is the result? Well, the result is lambda squared minus m squared over q squared plus m squared over times q squared plus lambda squared, right? So as you see, so if you have momenta q and masses which are much smaller than lambda, then you can ignore this, and then this cancels. Or another way of saying it is that this object that you subtract is much smaller than this, and you just ignore it. But when you reach momenta that are of the order of lambda, or more precisely larger than lambda, then in here you can ignore both m squared and lambda squared in the numerator and m squared in here, and then this goes indeed like lambda squared over q fourth. Okay, so that is the point about the Pauli Villars regularization. It is like the cutoff regularization, but it smoothly turns off the momentum. More specifically, the propagator now at large momentum behaves with a higher power of q. So it's not actually zero, but it goes to zero faster than the usual propagator. Right? So, all right. So, what does that mean? What does that mean? So, the point is, if you would have a theory that is not UV complete, for instance, you think that perhaps the standard model is not perhaps UV complete, that you need to add some more stuff to it. The stuff that you're supposed to add is very heavy, right? So, on one hand, what you could add in principle is very heavy stuff, but on the other hand, the thing that you want to subtract, the thing that you want to take out of your infinities are momenta that are also very heavy. So the solution of Pauli-Villars was to say, well, we just subtract this contribution of a very heavy particle that simulates as if you're doing something in the UV with your UV completing the theory in some point. I mean, this is the dumbest thing that you can think that tries to do that. All right. Okay.
So those CIs are just weights to?
Well, dimensional. This is one of a dimension one of a momentum squared, and here you have momentum. So this is supposed to go like lambda squared over q squared over q to a 2n minus 2, right? But how can that happen, right? If you don't put any CIs, well, you only get things like 1 over q4, right? In order to cancel all other kinds of terms, like 1 over q4, 1 over q6, 1 over q8, until you only leave this, you have to add some coefficients, right? You can try yourself to do this for n equals 2, and then you'll understand.
Right, I don't see it. But
Okay.
I mean, do they have to sum up to 1 or something like this? Is it just like
just
weights
do
over
it. Just do it for 2 equal n equals 2. Then you understand. You just literally add some CIs that depends on lambda and n squared, and try to find a behavior that goes like this. Just do it. It's an exercise. It's a very good exercise. All right. Good. So. Now, as I said, we substitute this with subtracting a propagator with a heavy mass. Now, this sounds silly because, of course, this doesn't exist. Doesn't exist a propagator with a wrong sign. Right? So how do you do this from the point of view of an action? Well, there's a way in which you can simulate Pauli-Villars. It's not Pauli-Villars, but something that smells like Pauli-Villars, and it comes from an action. By replacing this with adding a term that has a higher behavior with Q. You see, now, indeed, if Q is very large, I can just ignore this, and then the behavior is really lambda squared over Q4, right? But now, this is one over some stuff, which can appear from an action, right? If you remember, the usual action is integral d phi squared, and then you write this as 1 over 2 phi. You write it in Fourier space, 1 over 2 phi of p, then p squared plus n squared, and then phi of p, phi of minus p, sorry. Right? And the only thing you do now then to obtain this is to add here one more p4 over lambda squared. Alright? So now this comes from an action. I mean, this is the action in momentum space, then you have to Fourier back to X space if you want. But anyway, this is an action, right? So now this comes from an action and simulates Pauli with large.
But wouldn't this violate the dart or something because there is a quantity derivative? You can't have quantity derivatives in the
Unitarity. Why would you say unitarity?
or positivity of energy or something because there is a four derivatives.
No.
I'm pretty sure propagators can.
No, you're not. No. I think you're confusing various notions. The point is that this. So in momentum space, this would be this over this. And that is a good effective field theory term. That is perfectly fine. There's nothing wrong with it. Absolutely nothing. Let's. You're trying to talk about notions that we haven't discussed yet, but just trust me. There's no unitarity issue. This comes from effective field theory, which we will describe. And you'll see the kind of terms you could add, and it will work out.
I agree.
Okay. Anyway. Now another way that you could regularize would be to substitute not just the momentum, but the momentum squared to substitute with something. So let's say I have an integral over momentum So if I have this, if I have two propagators, right? So this was, for example, the example that I started with just now with an S, right? Now, in principle, I could try to substitute for each momentum. I can use Pauli lines. Well, that's one possibility, but another possibility is to substitute with the product of two propagators themselves, and then substitute the same thing with a large lambda. So So this is another possibility. And what does that mean? Well, that means that I have some integral that depends on m, right? This is an integral that depends only on m. Okay, it's divergent, but that's another story. And then from it, you substitute the same integral, but depending on very large lambda. Right? Yeah, I mean, you can sort of figure out that this is UV divergence, because here I have p to the fourth, and then yeah, at large momenta, you basically subtract the divergence of both. If you want to be more precise, you can figure out that this goes like lambda squared over p sixth. Right? Instead of 1 over p squared, it goes like the next possible power, lambda squared over p sixth. If you put coefficients here and here, you could have even smaller, but of course that's not the point. So now you have this, but now you can think of calculating this result, which is now convergent. So this integral defined like this. So I wrote it like this, but really it's integral of something, and that integral itself is convergent. So to calculate this object, I could, since it depends only on m and lambda, I could take the derivative with respect to m squared. But this object doesn't depend on m squared. So what you're doing is actually you're doing this. And you're noting then that this is convergent. Right? So now to be more precise, let's do it. So ddm squared, as I said, in acting on this doesn't give anything. And acting on here, you obtain, from the integral, you obtain 1 over so p squared plus m squared cubed. And right, so sorry, there's a factor of 2 here, so minus 2. So minus 2 over p squared plus m squared cubed. So now, indeed, the integrand behaves like 1 over p sixth. So it is indeed convergent. And, well, you can calculate this if you want, blah, blah. But, but then now that I've shown, so the result of this, well, you find it in the notes. It's minus 1 over 8 pi squared 1 over 2 m cubed. Integral of this. Now, so if ddm squared of this is equal to this, then that means that the original I of m squared and lambda squared, which was I of m squared minus I of lambda squared, this is just integral over integral dm squared of this result, right? So by doing this, you obtain 1 over 16 pi squared log lambda over m squared. And note note what we've done here. Well, so the result seemed to have been a trick, but in fact, what we've done is a different kind of regularization. So this seemed like a variation of Pauli-Villars, where I changed the product of two propagators with the same minus the version with high lambda. But in fact, what you've done is what is known as derivative regularization. Right? Because in all of this, there was no need for this thing, right? The only thing that I did in here was to note that this minus this now gives a convergent integral. But other than that, in terms of actual calculation, this term did not contribute. The only thing I've done then is really to do the derivative with respect to m squared of your divergent result. And then you get something convergent, which you can integrate back to a finite result. Right? So really what I've done is I've written that dd m squared of this integral d4 pi 2 pi 4 1 over p squared plus m squared squared, right? The only thing I've done is to note that while this is divergent, if I act with this thing here, I obtain minus 2 over p squared plus m squared cubed. And now the integral is convergent. Then I've calculated here, and then I integrate it back to a finite result. So the point is that by doing ddm squared, you have subtracted. So this in principle is a finite result plus a divergence that is m independent. Right? The divergence is at high m, at high p, where m is irrelevant, and so the divergence is m independent. So all you're doing is by doing the derivative with respect to m squared, is getting rid of the divergence. Right? All right. All right. So finally, we come to the most relevant regularization, and the one that in 99% of cases people use, which is dimensional regularization. So, this was invented by Hoft and Veltman because Hoft and Veltman have noted, so their contribution to physics, for which they got the Nobel Prize, was to show that the theory of Young-Mills, or gauge theory, is well defined, and in particular that you can regularize it, and then they thought, well, how do I introduce a regularization that respects specifically the gauge invariance? All right, and they found that the result is rather bizarre, but it works. So, well, I'll make some small comments at the end of the lecture of where it is that it's somewhat cumbersome, but so the point is that you work in D dimensions, but D dimension now is a continuous variable. Okay. So, more specifically, you would write that we are in D equal to 4 plus or minus epsilon. We'll see what plus or minus means, but for the moment, let me just say 4 plus epsilon. We'll see later on what you mean by plus and minus. So, to understand what this dimensional regularization means is to look at a function that appears very often when you do, I mean not very often, but always in fact when you do loop integrals, which is the Euler gamma function. All right. So, what is the Euler gamma function? It's an extension of the factorial. So, n factorial, as you know, it's the product of integer numbers, consecutive integer numbers, right? But Euler introduced a function that basically generalized this to the complex plane. So he wrote the function integral. Well, you can define it in several ways, but the way that is useful to us is to write it as write it like this. So integral of some variable, real variable, from 0 to infinity. Alpha to now z is a complex variable, minus 1, e minus alpha. And well, you can check for yourself rather easily by doing induction that gamma of n minus 1, sorry, n plus 1 is equal to n factorial, right? So indeed, this agrees with n factorial for some value. So when z is an integer n plus 1, then we have n factorial. But then we generalize this n plus 1 to a complex z. And of course, for factorial, we had that, you know, so if this is z, then we would say, so for z equal to n plus 1, we would note that gamma of z plus 1 so if this z plus 1 is n plus 2, then this would be n plus 1 factorial. So the first term would be n plus 1, which is z. So it would be z gamma of z. So this is certainly true for n factorial, but you can actually prove that it's true over the whole complex plane, right? All right, so that shows us what we're supposed to be doing. Well, we will obtain results that by putting d not to 4 but to some real and continuous variable, we will obtain an integral of the type of Euler, which will generalize the result in 4 dimensions and will have such a property. Now with this property, I can do the following. I can say, let's say, so the point is that I have to consider some epsilon going to 0. But if I have epsilon gamma of epsilon, so z gamma of z, this would be gamma of 1 plus epsilon, but epsilon is small, so this is approximately gamma of 1, which would be 0 factorial, which is 1, right? So that means that gamma of epsilon is approximately 1 over epsilon. Okay, so that means that now I've found a way to calculate some divergent object, regularizing with my epsilon in the dimension, right? So gamma of epsilon will be something that will appear, and it goes like 1 over epsilon, so goes to infinity when epsilon goes to 0. Then we can continue this and find similarly. So yeah, you put here 1 minus epsilon, sorry, minus 1 plus epsilon, and here minus 1 plus epsilon, and then here is gamma of epsilon, right? Which you already found, it's 1 over epsilon. So and this thing is 0, so gamma of minus 1 plus epsilon is minus gamma of epsilon. So that's also divergent. And you can continue like this, that gamma of minus 2 plus epsilon now would be 1 over minus 2 times gamma of minus 1 plus epsilon, and so on. By induction, you can find that all of gamma of minus n plus epsilon, they're all divergent. They're all divergent, more precisely like 1 over epsilon. And specifically, we will find in dimensional regularization, we will find exactly these kinds of poles. We will find gammas of this type, gamma of minus n plus epsilon, which will all behave like 1 over epsilon. Okay, so now examples. Yeah. So the simplest example that we want to consider is this tadpole, this one loop divergence in phi-4 theory, which is just a propagator integrated. So integral. So now we'll remember that we write things in the dimensions. Okay. All right. So how do we calculate this? Well, we can write this. Remember that I want to obtain the gamma function, which has this e minus alpha. So one way to do it is to write this as an integral that involves e minus this. So I write this as an integral from 0 to infinity of d alpha e minus alpha p squared plus n squared. Right? So now it looks better. Right? So first of all, I have to write this as the volume of the unit sphere with d minus 1 dimensions. And then times dp times p to d minus 1. Right? All right. Now m, I want this to be outside for a moment. I want to do the integral over dp. Now I have e minus alpha p squared, so now this integral is certainly convergent. So I write this as integral 0 to infinity d alpha e minus alpha n squared then I have omega d minus 1 over 2 pi d. And then integral 0 to infinity dp p d minus 1 e minus alpha p squared. Right? Now, to get to this form, I have to have integral d alpha. So I redefine this as x, p squared as x. Actually, yeah, I can put with alpha itself. So, so alpha p squared as x. Then I have that dx is 2 alpha p dp. All right. So dp is, so this is dx over 2 alpha p. All right. And let me write it like this first, and then so the dependence with alpha. Here I have alpha to the d, but p to the d, but this comes multiplied with, so p comes multiplied with square root alpha. So this is 1 over alpha to the power d over 2. Then I have here dx over 2p, and this is then x to the d minus 1 over 2, and this is square root x. All right, so this is square root 0 infinity d alpha e minus alpha m squared omega d minus 1 over 2 pi d alpha to minus d over 2, and what else? There was another 2 in here, and here I have integral 0 to infinity dx e minus x to the power d minus 2 over 2. Let's see, did I got this right? Yeah? Yeah. All right, so this integral in here that we got is indeed a gamma function. And specifically, if you look at the power, so gamma of z has the power z minus 1 in here, and you can write this as d over 2 minus 1. So this is gamma of d over 2. then the volume of the sphere in d dimensions, so omega d is 2 pi d plus 1 over 2 divided by gamma d plus 1 over 2. Now, this formula you can just test. So if I put, say, d equal to 1 for the circle, then I get 2 pi to the power. Here I get 1, and downstairs I get gamma of 1, which is 1. So this is indeed 2 pi for this. Then for 2, I get 2 pi to the 2 thirds, sorry, 3 halves, divided that over gamma of 3 halves. But remember that this is 1/2 times gamma of 1/2, and gamma of 1/2 is square root pi. So by doing this, so square root pi cancels the 1/2 from here. We're left with pi, and then the result then is 4 pi. So indeed, the volume of the 2 sphere is 4 pi, and so on. You can check this formula. So then the final result is omega d minus 1, so that's 2 pi d over 2 over gamma of d over 2. And then in here we had gamma of d over 2, so that cancelled. But finally we're left with integral 0 to infinity d alpha e minus alpha, and then alpha to minus d over 2. Now this thing, remember, the power here is z minus 1 for gamma of z, so this is minus d over 2 plus 1. All right? So this result is now divergent because if I put d equal to 4, I get minus 2 plus 1, that is gamma of minus 1, which, as we said, this is divergent. Moreover, also as we said, the divergence in here goes like 1 over epsilon, right? And I've missed somewhere the powers of m. Oh yeah, sorry. Yeah, it was alpha m squared. So I have to multiply and divide by m squared. So the power is d over 2 minus 1. So m squared by d over 2 minus 1. Yeah. And Oh, yeah, and I also forgot that there was 1/2 pi d. Yeah. So now it works out. You get indeed 1/4 pi to the power d over 2. All right. And then, moreover, I can take derivatives with respect to n squared of this integral. So this is a particular Feynman diagram, right? But the kind of integrals that appears in Feynman diagrams include integrals with more propagators. So in particular, I could have something like this. I could have an integral with n propagators. And to calculate this, I take n minus 1 derivatives with respect to n squared. And then I find the results that I have in the notes. Let me write it somewhere. Perhaps here on the left. So integral d 2 pi d 1/p squared plus n squared n equal to gamma n minus d over 2 4 pi and gamma of n m squared over 4 pi d over 2 minus n. Note that while the gamma function appeared in here, this is only divergence for n equal to 1. For n equal to 2, 3, and so on, it's all convergent. But nevertheless, these kind of integrals do appear. So this is something relevant. All right. So now I've shown to you how to do the simplest loop integral, right? The integral with one propagator. But of course, when you do calculations, you have more propagators. So the question then is, how do you do such integrals? And for that, we do what is known as dimensional, as a Feynman parametrization for the dimensional regularization. So all right, so let's consider the next complicated thing, and then we'll go to the general case. So the next complicated thing would be when we would have a Feynman diagram with two propagators, like this. So this would be a one loop 2-point function in phi 3 theory, right? So, well, the integral that we will consider here would be integral p, and oh yeah, perhaps let me call it q now. So let's say this is q, or yeah, no, like this. I define it like this. This is p. No, on the contrary, like this. Yeah. Then this is p plus q. To stick to my convention. So this would be q squared plus m squared for this propagator, and for the other one, q plus p squared plus m squared. So you see, now the problem is not that you have two propagators. I mean, here, apparently I wrote several propagators, but you know, there was not. This was this is just an integral that appear in calculations, but this would be the same propagator. Whereas in here, in the physical case, you have propagators with different moment on them, right? In here q, in here q plus p. So the trick of Feynman is to rewrite this then as something of this type. As so instead of having a bracket times another bracket, to have a single bracket squared. Okay, that's basically it. And the answer to this is to use this simple integral relation that 1 over delta 1 plus delta 2, meaning the two propagators, is integral from 0 to infinity of d alpha 1, 0 to infinity d alpha 2, e minus alpha 1 delta 1 plus alpha 2 delta 2. Right? This is well, this is basically the same thing that we did here, right? Here, when we had one propagator, we wrote this, and now we just do the same for both propagators. But if that would be the case, we wouldn't win anything. But now that we have two integrals, we could do a redefinition of the integration variables. So the redefinition that we can use is alpha 1 is t1 minus alpha, and alpha 2 is t alpha. All right, so that's the important point. And then the Jacobian for this is 1 minus alpha, alpha minus t, which is t1 minus alpha plus alpha t, so this is just t. So the Jacobian for the transformation is just t, so I can just rewrite this as integral 0, 1 d alpha. As you can see, in fact, alpha now varies from 0 to 1 because here I have 1 minus alpha. But t now varies from 0 to infinity, as did alpha 1 and alpha 2. So dt t2, well, there's 1 from the Jacobian. Sorry, yeah, just 1 from the Jacobian, and then e to minus. So alpha 1 is t1 minus alpha. Delta 1. And alpha 2 is t alpha delta 2. All right. So this is well, sorry. Yeah, I can do the. I can put t as a common factor. And now I have the same integral that I had before. So this is now indeed 1 over something squared. Right? Because this was, as you remember, gamma of z well, whatever. The point is that here you have to integrate by parts, and you obtain to get rid of t, and then you get this 1 over this factor, and then you have the integral that we had written before, the integral of just d alpha times e minus alpha something. So the final result here is just so 1 over delta 1 delta 2 is integral 0 infinity d alpha then we had 1 minus alpha delta 1 plus alpha delta 2 squared.
Sorry, Professor, this integral shouldn't be going from 0 to 1 instead of
Oh, with 0 to 1, sorry. Thank you.
You just did the integral over t.
Sorry?
You just did the integral over t.
Yeah, just the integral. So yeah, I wrote here 0 to 1, but I forgot to copy it. But if you just had 1 over something squared, that wouldn't be so interesting. What is interesting is if that bracket is of this form of some q squared plus something else, right? In other words, that there's no term that's just q dot p. So I have to get rid of such terms. So let's write this specific. Let's write this in detail. So So delta 1 was q squared plus m squared. And this was q plus p squared plus m squared. So I have q squared here, q squared here, coefficient 1 minus alpha, coefficient alpha, so I have q squared. That's good, but then, as I said, now we have q dot p in here. Coefficient 2 alpha. And then I have m squared with 1 minus alpha plus alpha. So this is plus m squared. Right? But then we rewrite q as q tilde minus alpha p. So by doing this, I cancel the linear term. So this is written now as q tilde squared plus m squared. But then from this, I will also get a p squared term. So from here, I will get alpha squared. And from here, I get minus 2 alpha squared. Okay, so, and I'm still missing an alpha, which is where is the alpha? From the no, I forget. Well, okay, I'm too tired to figure this out where this is, but the result is p squared alpha 1 minus alpha. So I can see minus alpha squared because it's alpha squared from here, then minus 2 alpha squared from here, but I don't see the other alpha. Anyway, it's from somewhere. All right. So the final result for the integral is I is equal to integral from 0 to 1 d alpha, and then integral over q, which was what I wanted to do, 1 over this thing squared. And the integral over q is shifted to integral over q tilde. And then I can write this as omega d minus 1 q tilde d minus 1 dq tilde, and well, but more precisely, I'm sorry, yeah, I don't even need to do this, being silly. I just apply this formula for n equal to 2, right? If I have n equal to 2, and instead of m squared, now I have this thing, m squared plus p squared alpha 1 plus alpha. So I just apply this, and the result is so the result is gamma of 2 minus d over 2 over 4 pi d over 2 integral 0 1 d alpha, and then alpha 1 minus alpha p squared plus m squared to the power d over 2 minus 2. Right. Well, I have some integrations in here that I will probably skip. Yeah, I'll skip because I don't have enough time. You can calculate similar integrals by putting let's say m1 here and m2s here. I can do similar steps to arrive at an integral that you would call I11, which has one propagator of mass m1, one propagator of mass m2, and then act with dd m2 squared as before to go to I12, and then generalize to I1n. So with one propagator with mass m1 and one propagator with mass m2. Yeah, so, but I don't have time to do this. So, so what we want to do is to do a general formula for Feynman parameterization. So you see, what did we do here? So the first thing we did was this, was a loop with, well, there were two lines coming out from here, but perhaps that's not so relevant. Now there's a loop with 2 points at which one line comes out. But again, whether it's 1 or 2, it's really not that important. But the general integral that we would be interested in, general one loop integral, would be one where you have this one loop, and we have n points along the loop, and at each point you have, let's say, 1 or 2 lines coming out, but in any case there's some momentum P1 coming into the from the outside, right? So here I have P1, here I have P2 until Pn, and again I have a loop integral Q that that starts enters into the first point P1. So in this case, so in this case, the integral that we want to have is integral over this loop momentum, integral dq over 2 pi d, and then a product of propagators, each one with loop momentum q and well, some p tilde I squared plus n squared. Yeah, actually this, no, I write it correctly, yeah. So the point is that that there's, here I have P1, here I have P2, but then momentum here is Q plus P1, whereas in here is Q plus P1 plus P2, which I call P tilde 2, and so on. So these P tildes are just sums of the external PI's from 1 to n to I. All right. Okay. So now I have this n propagator 1 over delta 1 until delta n. And so I continue to do the same thing I did before. Each 1 over delta I write as an integral over minus alpha delta. So integral well, pi I equal to 1 and integral 0 infinity d alpha tilde 1 e minus alpha tilde 1 delta 1 minus alpha tilde n delta n, right? So each propagator I have written in the same way as before, but again the crucial point now is that we switch integration variables from this alpha tilde n's to an overall t that goes from 0 to infinity, and some alpha 1s that have a finite range. So let's say I write alpha tilde 1 is alpha 1 t, and until alpha tilde I is alpha I t, and so on. But remember that I need to have n integration variables. So t is an extra integration variable that means that I have to have a constraint on the alphas. The constraint is that they sum to 1. So before I had alpha and 1 minus alpha. Now I say that the sum of all the alphas is 1. Alright? So that means that certainly alpha i's are smaller than 1. And again, I can calculate the Jacobian and find that in this case is t to the n minus 1. So, now I have product from 1 to n integral delta alpha I from 0 to 1, but also with delta sum alpha I minus 1. And then I have still the integral over t from 0 to infinity, t n minus 1, e minus t now is a common factor as before, and then I have alpha 1 delta 1 plus dot plus alpha n delta n. Right? All right. So this integral is easy to figure out. This is so I just scale out by this bracket. So I multiply and divide by it. Here I have t to the n, so I'll have the bracket, so 1 over this bracket to the power n, certainly. And the result is integral dt, integral dx, x n minus 1, e minus x. And as you remember, that's the gamma function. So that's gamma of n. Okay? All right. So now just a moment. What I want to say. Yeah, I think I skipped an a step in here. So the point is that as before, when we write this in components, you'll find. So here I have q squared plus m squared, and then in each one I will have q plus p tilde I squared plus m squared. And so the coefficient of q squared is alpha 1 plus alpha 2 plus alpha n, which is 1. So then I have q squared. But then I have q dot times. And in each one I will have what I defined as p tilde I. So sum over I, p tilde I, factor 2, then plus m squared, and oh no, sorry, I actually have this here as well. All right, and yeah, there's a factor of 2, but I missed, but no. Oh, that's right. Anyway, and then I have to switch then integration variables from q to q tilde, but q tilde minus sum over alpha I. Oh, sorry, yeah, this one is with alpha I. Yeah, so sum over alpha I, p tilde I. And when I do this as before, this term cancels. So in here I will get 1 over q tilde squared plus m squared. But then plus, I get the extra terms, which this time they are sum over alpha I p tilde I squared minus sum over I alpha I p I everything squared. All right, and that's before I change the integration variable from q to q tilde, and also as before I use this formula that I kept on the blackboard, integral over a variable 1 over p squared plus something to the power n. So now I have integral q tilde 1 over q tilde squared plus something. Something is now m squared plus this combination. So finally then I get the general one loop general one loop integral, which is, so from this I get gamma divided by this, so gamma n minus d over 2 over 4 pi d over 2. And now I have the problem, integral, integral d alpha I delta 1 minus sum over I, and then squared plus sum over I alpha I pi squared minus sum over I alpha I tilde squared power 3 over 2 minus 2. Okay, so this is the general one loop integral, one loop Feynman diagram. Now, is this solved, do you think?
What so?
Is this solved? I mean, have I solved the issue of the divergence, and have I calculated the leading part, do you think? No, right? I didn't, because this one, remember, is not divergence. It's not divergent. It's only divergent for n equal to 1, but n equal to 2, 3, and so on, it's not. Right? Well, so there was no, depending on the dimensions, but it's not actually divergence, but the problem is that I cannot, in general, calculate this with the constraint over alphas, right? So I have to, so in principle I can calculate the integral over alpha 1, the integral over alpha 2, alpha 3, and so on. But when I go to the last alpha, it's usually, that's where the problem comes. So this formula is useful, but it's not the end of the story. You still have to do a lot of work to do something. So for one propagator and two propagators, I've showed you how to do it, but in general, it's more difficult. Now there's another alternative parametrization, alternative Feynman parametrization. So as I said, the first step is to write the propagator as integral d alpha e minus alpha times the propagator. But the parametrization itself is changing the integrals from the integration variables from the alphas, well, I guess I call them alpha tildes initially, to the new integration variables, which now I call them t and alpha. And the integral over t is from 0 to infinity. I can do it and obtain this power, this new propagator-like thing to some power n. But the integrals over alphas are a problem. But in this particular parametrization, I have all the integrals over alpha I are from 0 to 1, with the caveat that I still need to use the constraint that the sum over alphas is equal to 1. However, I can basically solve the constraint by redefining alphas in the following way. Let me erase here. So I can rewrite alpha tilde I, sorry, alpha tilde 1 as T1 minus alpha 1. That's really what I started with in the case of two propagators. But then alpha tilde 2, I write T alpha 1 minus alpha 2. Alpha tilde 3 as T alpha alpha 3 minus alpha 2 minus alpha 3, and so on until alpha tilde m is T alpha m. So you see, for the case of two propagators, I had this and this, and that was it. But now I introduced this extra stuff, and you note that now if I sum everything up, so the point was that that we got the constraint that sum over alpha i's was equal to 1, which means that so this was the original parametrization, which meant that sum over alpha tilde i's was supposed to be equal to just t, right? And now sum over alpha tilde i's is also equal to t, because this cancels with this with this with this, and so on. Right? All right. So, but now I have that alpha 1. Of course, because of this, varies from 0 to 1. Alpha 2 varies from now. So alpha 2 must be smaller than alpha 1. So 0 to alpha 1. Then alpha 3 belongs 0 to alpha 2, and so on. And the Jacobian is the same thing. It's still t to the m. So now the only thing that I have is, the only difference that I have is that I have integral from 0 to 1 d alpha 1, integral from 0 to alpha 1 d alpha 2, integral from 0 to alpha 2 d alpha 3, and so on. Then integral alpha n minus 1 to 0 to alpha n minus 2, and finally integral 0 to infinity dt, which is what I which is the same integral as before, meaning it's t to n minus 1 e minus t, and now the only difference is the alphas again. 1 minus alpha 1 delta 1 plus alpha 2 minus alpha 1 delta 2 plus blah 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 plus alpha n minus 1 delta n. Right? And again, this is this is again 1 over, as in this case, it's 1 over this bracket to the power n. The only difference is that the bracket now has this kind of new term. So alpha 2 minus alpha 3 times delta 2 and so on. So, so the point is that sometimes it might be easier to use Feynman diagram, Feynman parameterization in this form in order to do the integrals of alpha, because the integrals of alpha are the problem, like I said. The integral of alpha is what impedes me to write this as a closed form formula. So I have to do things in each case. I have to work to do the integrals. All right? Good. All right, so this until now was the calculational part of dimensional regularization. Now let's go back and think a little bit about what dimensional regularization means. Yeah, let's see which is here. All right, so I have usually, I mean, I've been talking about scalars, so usually I would write something like this: g mu phi plus m squared over 2 phi squared plus lambda n over n factorial phi to the n integrated. Oh, yeah, important. Integrated over d. Right? So, since this is what appears in the path integral, I have e minus s, always. S is a number, so the dimension of 0 is 0. The dimension of S is 0. That means that the dimension of this thing must be d, since the dimension of this integral is minus d. All right? So, so let's look, well, either here or here. You see, here I have something of dimension 2 times dimension of phi squared. So that means the dimension of phi is equal to d over 2 minus 1, right? But then let's substitute in here. So let's say, so phi to the n, dimension of phi to the n is n d over 2 minus 1. But this bracket is supposed to have dimension d. So that means that the dimension of lambda is d minus this n d minus 2 over 2. Okay, that we had seen before, but we assumed before that b was, we assumed before that b was integer. But now that b is not integer, that is real, remember I said, let's say 4 plus epsilon in here, and here I have also 4 plus epsilon, right? So so that means that this thing, well, yeah, this thing has the dimension of epsilon is epsilon times 1 minus n over 2, right? The dimension, the rest is whatever it is, but the dimension of epsilon is this. Now, in particular, in 4 dimensions, the 4-point coupling is dimensionless, right? We've seen that last time. But now, the 4-point in d dimensions, this is n equal to 4 over 2, so 1 minus this is minus 1. So the dimension of lambda 4 in 4 plus epsilon dimensions is minus epsilon. Alright? So that means that suddenly, so let's assume for simplicity's sake that there was no mass. If there was no mass, that means that in d equal to 4, there was no any object with mass in here, right? But then how is it that I go into d equal to 4 plus epsilon and suddenly lambda 4 has dimension minus epsilon? Where does that come from? How, this is a quantum object, but it should depend on some parameter, or some parameter with dimensions of mass. Well, the thing is that we have to introduce such an object. So we introduce an object mu that has dimension 1. You can think of it as some mass. And we say that I have to multiply this. So I write, I will write lambda times mu to the epsilon, right? Now this has the correct dimension, right? And this object must appear in the quantum theory. So this fact that that we have to introduce a mass object is called dynamical transmutation. In this particular case, I can also say dimensional, since we're talking about the dimensional regularization. But the point is, now we go back to our first two regularizations, cutoff and Pauli Villars. There we had to introduce by hand some objects with dimension, a cutoff lambda, and some inverse mass, also lambda in Pauli Villars. But here is also the same is true. I have to introduce an object mu, also with dimension, in order to define the quantum theory. So this is intrinsic to the quantum theory. In quantum theory, I have to introduce an object with dimension. And the point then that we will explore in some of the lectures after that is that the physical quantities should be independent on this arbitrary object with dimension. And this is what we will be calling the normalization group flow. But we'll get there. The point I want to stress now is that we always have to introduce an object with dimension in order to define the quantum theory. All right. There is one more problem that that one can see when we do dimensional regularization. So I said that this is all nice and beautiful and respects Lorentz invariance and gauge invariance and also all sorts of nice things. But there is one thing that doesn't work so well for. When you talk about fermions, I mean, people have been introducing fixes for that, but it's cumbersome. Well, the point is, when we talk about fermions, we talk about gamma matrices, right? And well, you can always dimensionally continue things like this. The G nu, that's D, right? That's, you can make continuous. You could also, well, dimensionally continue if you have, as we saw, we have formulas like this for products of gamma matrices which reduce to smaller ones, basically by contractions of this type, right? These you can dimensionally continue. However, the point is that gamma mu's still satisfy the point is from here that the gamma mu still satisfy the Clifford algebra. However, it depends on the representation of the Clifford algebra, depends on dimension in a very specific type of way. Remember that I said that the dimension of the representation is 2 to the integer part of d over 2. There I kind of meant that in the sense that if I have 3 over 2 integer part is the same as 1. So the dimension in 2 and 3 is the same, and the dimension in 4 and 5 is the same. But now I also tell you that the dimension in 4 plus epsilon is also the same. So that means some problems, because you still have to, well, so the first thing is to be careful that the trace is still, so trace means sum over indices of the gammas, right? But the dimension is still 4-dimensional, so this is still 4 G minimum. So that's not a problem. But the problem is when you have to define things like gamma 5. So this is, as you remember, this was supposed to be, well, one way to define was that was I over 4 factorial epsilon mu rho sigma gamma mu gamma rho gamma sigma. But by writing it like this, again, doesn't help you much, because this is still a product of 4 gamma matrices. And well, you cannot quite then dimensionally continue this, right? This is supposed to be the 5th. The 5 here amounts to saying that if you work in 5 dimensions, this is the 5th gamma. Since in 4 and 5 dimensions you have the same number of components. But yeah, I mean, gamma 5, it's hard to dimensionally continue. And the point is that in the standard model we have chiral fermions that involve these projectors, 1 plus minus gamma 5 over 2. So introducing fermions, it's a little bit difficult. It's not completely impossible, but it is challenging. So all right. All right. So this is everything I want to tell you today. Next time we will see what to do with this infinities. So now we've regularized these infinities to something finite. Now next time I'll tell you how to hide them into things. All right. So do you have more questions?
What will change in the introduction of this mu if you have a non-zero mass? Because you started the argument.
No, I just said, yeah, it doesn't really. No, I just meant for the argument to be clean, I had to say, well, there's no mass, and therefore, it's obvious that you have to introduce a new mass. So the argument otherwise is a little bit more messy, because now you have mass and you can imagine you could put that mass in there. But no, in fact, you can't, because clearly that's a different kind of, large mass, if you want. So you always need to introduce an arbitrary mass scale. And the point of the quantum theory is that the physical result should be always independent of this arbitrary mass scale. So that leads to a so-called Cullen-Zimanchik equation that we're going to show later on.
Right, so it was just for us not to try to relate this mu with the mass, the original.
Yeah, I just want to say that I just wanted to make it clear that it's not related to the mass. Right. All right. Okay. So I'll see you then on Wednesday. By the way, so did the people fix it with Pedro?
Yeah, we'll have class with him today at 2 p.m. and then he'll tell us the full schedule.
All right. Good.
He hasn't decided yet the time for
Alright.
the next class.